Good afternoon, everyone. Hope you guys are doing very well, learning and enjoying LeProFesseUR lectures. In this lecture, we're going to be discussing about graphs. Graphs are very, very useful almost in every field of science, engineering. You can find uses of graphs, applications of graphs. So it becomes quite important to understand at least the basic concepts behind graphs. So let's try to understand what does it mean, what the graphs are. Let's talk about some few simple real-world applications. Okay, let's say you in your friend circle you have many friends, or you may not have many friends, but you know someone who knows other friends, so your social circle is quite big. Maybe big, may not be, okay, nevertheless. And you are hired by a social media company, okay. The business for social media companies, or the people who are in the business of social networking websites, or providing the facility for people to interact with each other. Their business is dependent on how effectively they make use of interactions between people, or how effectively they can make use of the information exchange between different people. So essentially, they want to analyze what sort of communication is happening between different group of people, so that they can display targeted advertisements, which is their main bread and butter. Okay. So if you don't know graphs concepts, it will be very tricky, harder to get job in a company whose business is dependent on these kind of activities. So nevertheless, even though if you're not planning to go to social media companies, in other fields too, graphs have very much use. But in this context, let's say this group of friends, Harry may know Hermione. Okay, so there is a connection between Harry and Hermione. Okay, Hermione may know Anjali and Floyd. There is a connection again, and you are linked with Anjali and Floyd indirectly through Hermione. Okay, and Floyd may know Randy. So essentially, you are connected with all these people at a different level. So first level you are connected with Hermione, second level Anjali and Floyd, and third level Randy. Okay, and if you are say on a social media website, you have your profile there, and you are engaged in chatting, texting, communicating, sending email messages, and knowingly or unknowingly you had given permission for these companies to use the information what you are exchanging between people. So that's sort of not very ethical, to store information or private communication or whatnot, what people are having. But nevertheless, the companies, they store each bit of communication what you are exchanging between different people, and they make use of they analyze that information. And how to effectively analyze? Well, that's a tricky problem, but we can model these problems. Let's say a person is a node, okay, and if there is a connection between X person to Y person, then you make a link. So this node or person becomes a node in a graph, okay, and the connection between two people becomes an edge or an arc in a graph, right? So if you can analyze, if you can build up that whole big graph, okay, and analyze the information exchange between people, you can effectively make use of that information. Okay, so that's basically a typical example of social network analysis. All right, let's try to see another example. Let's say I live, Toronto is my hometown, I live here, and I like to travel. I like to visit many countries, like to visit different cities, and for next year I have few cities on my list to visit. Okay, so I plan to go to Germany, Munich, for example, Seoul, South Korea, Venice, Italy, Paris, in France, Rome in Italy, and Agra. Want to see Taj Mahal, one of the 7 wonders of the world in India, and I have only limited budget. So, and I want to see all the cities. So essentially this problem becomes that I want to find a minimum cost route, okay, so that I don't have to visit a city twice, all right, and I come back to my hometown, Toronto, the minimum cost possible. How it is? Say I have choices that I can fly from Toronto to Rome, or Toronto to Agra, or Toronto to Munich, or either way, like say I fly from Rome to Paris, Paris to Agra, right? So different connections are possible with the different cost. Cost here, we can simplify that. We take a cost like flight ticket cost, okay? So ticket cost may be different for different routes. Say it might be different for going from Toronto to Rome, but while coming from Rome to Toronto, it might be different cost. So how do we solve that problem? Okay, think about each city as a node, okay, node in a graph. And if there is a flight possible between two cities, we connect it via an edge or an arc. So let's try to formalize, hypothesize our hypothetical example. Okay, so there is a flight connection possible from Toronto to Rome, Italy, direct flight, or I can go from Toronto to Paris. Okay, I can also go from Toronto to Munich, and I can also go from Toronto to Agra. Now these flights may have different cost, okay, along the different routes, right? And there is another possibility from Rome to Paris, okay, Rome to Venice, Paris to Seoul, Paris to Munich, Paris to Venice, Venice to Seoul, and Munich to Agra. Okay, so different possibilities, different cost along each route. Now, say this is another typical example of a graph. Now notice here, we do not have any direction in this graph. It means that we can go from Toronto to Rome, and we can come back from Rome to Toronto back. Okay. So think about when we have say different cost on each edge, and we try to formalize or try to develop a mathematical formulation. Essentially, we want to optimize the cost. So in the end, it will become a function and it will become an optimization problem. But nevertheless, such kind of problem we talk about or we classify such kind of problem under the domain of TSP, traveling salesperson problem. Okay. Now let's see if we have directed arcs. We can go from Toronto to Rome and Rome to Paris, but we cannot come back from Rome to Toronto. So that becomes an example of a directed graph problem. And we can further have the weights, okay, weights along each path. Weights are nothing but the flight cost. Okay. So say for example, we are flying from Toronto to Rome, it might cost $500. We fly from Toronto, we fly from Agra to Toronto, it might cost $900. So we may have different costs associated, okay, with each route. Let's see how this problem turns into a directed graph problem. So similarly, many other situations are there, or many other applications are there where you can make use of graphs. All right. So let's try to understand what graphs are. Understand what are graphs in simple sense. Graph is nothing but the nodes and the connections in between nodes. To nodes, we call it vertices, represented by V, and connections between nodes, we say edges, or by A. For example, let's say we have these few nodes, bunch of nodes, and we have these connections in between nodes, right? What we can say? Okay, so here G, V, E means V means I'm just representing in a short form, means how many number of vertices a particular graph has. So here in our example we have 5 vertices, okay, 1, 2, 3, 4, 5. And we have how many edges? 1, 2, 3, 4, 5, 6 edges, okay. So we can also say that G5, 6, okay. And if we want to analyze the time complexity or space complexity for graphs, we can simply say big O notation, in big O notation, O of VE, where V is vertices, number of vertices, E edges, or we can also represent in that form, okay. Either way. Now understand that those who are not familiar with the complexity, we discussed what are complexity in terms of algorithm analysis in the very first lecture or second lecture. You may go and watch previous lectures, or in simple sense we want to know some kind of estimate for time complexity. We want to know some kind of estimate about how much memory our program or algorithm gonna take, means space complexity in simple sense. All right, so let's say how we can represent this graph, okay, how we can represent, or if we are talking about programming and whatnot. So what we can do, how we can represent? We can represent either via matrix. Let's say this matrix. Now here matrix has row and column. It's a square. So whatever number of vertices you have, that many number of rows, that many number of columns you will have. And how we have put this matrix like 0 and 1. Let's say if there is a connection between two nodes, means we put the 1, indicating there is a connection. And if there is no connection, we put it 0. For example, there is a connection between A and B, so we have put 1 between A and B, right? In the same way, let's say there is a connection between C and B, so let's say B and C, okay, we have put 1. And in the same way, from C to B, it's a connection. So we can fill it up, this whole matrix. Now notice here that this matrix, like if we store the each 1 and 0 in some storage box or memory location, how many total memories we would need? So we have 5 vertices, so 5 multiplied by 5, so that many 25 storage box we would need, or 25 memory locations we would need, okay. We can also represent the same graph using lists, collection of lists. List is another kind of data structure. Same way like matrices, you can use a two-dimensional array to create this matrix. Same way we have lists, okay. So how we can use that? Let's say simply the nodes, okay, in a list. So this is pointing to another nodes, and these B and C, this whole thing is a linked list, okay. And in this linked list, A is connected with B and A is connected with C. That's what it is indicating here. Same way, another list for node B, okay, node B. Node B is connected with A, connected with C, connected with E, right? So we can fill it up all other entries for the list. Now, interestingly here, notice one thing. If you need to have memory locations for this list to store in memory or storage boxes. How many boxes would you need? Well, basically, if you count it, it turns out to be twice the edges. Okay, so 1, 2, 3, 4, 5, 6. So 6 edges multiplied by 2, and the first column is just nothing but representing the number of vertices. Okay, right. This is V plus 2 times E. All right. So that is in the case of list, but in the case of matrix, what we had here, V multiplied by V, right? So what we can deduce from this in terms of the storage requirement for this graph, two different ways of representing it and two different ways of storing it. Okay, so in terms of matrix, we can say that the space complexity would be in the order of V square, okay, where V is number of vertices, and in terms of lists, we can say that order of V plus E, where V are number of vertices, E are number of edges. So you can see that we have certain advantage when we use list structure, okay, that we can store in less area. However, as you know, if you have watched previous lectures, that linked lists are relatively slower compared to matrices. Okay, so here, if you represent this graph via matrices, you need more locations or your memory requirement is more. Okay, but basically your algorithm can be faster compared to linked lists. Searching and sorting in linked lists are costlier operations. Anyways, so there are situations where you may want to prefer to use list, and certain situations where you may want to prefer to use matrix, right? And this is, by the way, this is undirected graph. There is no direction on the edges. Okay, so one can go from A to B and B to A. There is no direction. Okay. Another interesting thing here, let's say if you have an arc or an edge which is just a loop on E, how would you represent it? Means E has connection to itself, means E and E has connection to itself. So instead of 0, you will put it 1, and in the same way you will append it here that E has one more connection for itself, right? I will make this connection. The pointer is just playing around with pointers. So basic idea is that to understand how you can represent this in memory, okay, or you can create data structure for the graphs. All right, so let's talk about what if there are direction. Okay, the previous example we saw that there are no directions, undirected graph. Now what if we have directions? We can only go from one node to another node and not coming back. Okay, so let's say we can go from A to B, and we can also go from A to C. Okay, we can go from C to B, and we can go from B to E. Okay, and we can go from E to D, and we can go from D to C, right? And so now in this structure, what we're gonna do, how we will represent it. So you see, wherever there is a connection from A to B, So let's say A node has a connection to B, we will put 1. Okay. A has a connection to C, we will put 1. Okay. Now B doesn't have a connection to A, so we have put 0. But what if B has a connection to A? Then we will put it 1 here. Okay. In the same way, we have adjusted other entries. Now B doesn't have a connection to C. B doesn't have a connection to C. I mean, it has a connection, but not from B to C, from C to B. Okay, this is a directed graph, so we have put it 0. So we can fill this this whole matrix. Now notice here we have most of the entries 0 and very few entries are 1. So this turns out to be a sparse matrix. Now think about if we have to store all 25 locations or 0 and 1, we are basically, we can say that we know there is no connection, or we cannot go from say A to A or B to A, it's all 0, but we are wasting the memory space. So in that situation where we have sparse matrix, we can use a list structure. Okay. This filling up of the matrix, we can also say that if Aij is the element of this matrix, and if it is 1, if there is a edge from I to j belongs to E, means edges of this graph, and 0 otherwise. Okay. And how do we represent it using list? Same way. Say nodes, yeah, put it in one list here. You may use it as an array, this first column, or list, either way, whichever you like to implement it. And A has a connection to B and A to C, right? Now here B has only connection to E, so we just have one connection here. C has only connection to B. Okay. D has only connection to C, and E has only connection to D. Okay. So see the memory requirement here. For the matrix representation, it doesn't change, same in the order of V square, but here it's still like V, number of vertices, plus number of edges, right? Now here it is reduced, of course, because we are using the direction on the edges, but still it's in the order of V plus E. So what we can say for this kind of scenario, that the adjacency matrix is preferred for dense graphs. Okay, or in other words, where number of edges are very close to square of vertices, and lists are preferred for sparse graphs. Okay, where number of edges are very, very less than a square of number of vertices, right? Now let's say, for example, here you can go from A to B and you can come from B to A. Okay. So you have to make necessary adjustment, that B to A, instead of 0 you will have to put it 1 here. Okay, and you have to make one more. You have to add one more element to this linked list. Okay, denoting that you can come from B to A. All right, very simple. This is for directed graphs. All right, now what if we have some weighting on these edges? Let's say in our say tour example, that I want to go from Toronto to Miami or Toronto to Venice, and I can put some cost that if I go from Toronto to Miami, I have to spend $1,000. Or if I go from Toronto to Venice, I've just spent $500, right? So what if we put some weight on the edges? Okay, how we can represent it? Say, for example, we have put some weights on different edges in this graph. And if we want to represent it via matrix, how we can represent it? It's very simple. Instead of putting one where there is an edge between two nodes, you just simply use the weight, and it is implicit that there is a connection. You can go from A to B if there is a weight. Okay, so how simple it is, right? Rest of the things are same. Nothing is changed. Okay, and how you can represent it via list? Well, it's again very simple. Now, instead of having the information about the node, that A node is connected to B node, means you can go from A to B, but along with that information, you want to store the weight as well. What is the weight on that edge going from A to B? And what is the weight on the edge when you go from A to C? You will store in this next location in the linked list along with the C. Okay, and rest of the entries you can fill it up the same way. Okay, now this is W5, last one. The color doesn't show very well. It's W5. Okay, so see how simply we represented the graphs. Okay, now in graph algorithms going forward, we're going to be analyzing complexity in terms of V and E, how many vertices, how many edges. Okay, and it's just fun to play around with the graph algorithms, right? Another important thing comes that how about, so here we have used the attributes on the edges. Okay, like say cost of the edge. There can be many other attributes. Now we didn't discuss about how to put attribute on nodes. Okay, now there can be different ways to put attributes on node. That is more implementation oriented. Okay, you can make a separate list of nodes, a structure, or you can, like in modern programming languages, say C++, you can make it a class, and the node object itself is containing bunch of information where you can fetch node's private members. Okay, that information. So it's sort of implementation oriented, but in terms of algorithms, we don't specify as such. We just node, and you can associate what information in whatever manner you want to associate it. Important thing is the connection between nodes. Okay, how many nodes are there, what are the connections are there, whether there is cycle, acyclic, cyclic, and there are many concepts which got evolved when in the last maybe 50 years, 100 years. You can check on history. I'm not going to go into history, but the idea here is to understand the simple concepts, okay, so that you can get along further and develop some interesting algorithms, or just understand what graph algorithms are. All right. So thank you very much, guys. Hope you have enjoyed this lecture. Thank you for subscribing and liking lectures on YouTube. Those who have not subscribed, please subscribe LeProfesseur channel on YouTube. We appreciate your support. And as I always say, algorithms are everywhere. Remember that. Have a wonderful day.